Let me elaborate on this again, really quick. So think about this for a minute. I want a series to converge and the absolute value to diverge. If the series is positive, do you see that the absolute value wouldn't change the series? And if it's the same series, how could it be sometimes convergent, sometimes divergent? So when I look at number 32, since that's negative, maybe the absolute value will alter the problem and make that positive. That could be conditionally convergent. 34, there's no way it could be conditionally convergent because the absolute value doesn't change the nature of the problem. If you put an absolute value on this, that's not needed. So therefore, there's no way number 34 could be conditionally convergent. The only way you could have a series that could be conditionally convergent if the absolute value changes the nature of the problem. And let me show you, and as you can guess, I want to look at number 2. Number 2 right there. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. Well, let's look at the absolute value. The series of 1 over radical n. Absolute value eliminates the negative 1 to the n minus 1. Hey, I know what that is. That is the series of 1 over n to the 1 half. P equal 1 half less than 1. Therefore, diverge. So if I glance at this rule, it diverge. Okay, now what? Does the original converge? If I take the limit, before I get too excited, can't I say this is positive, decreasing, and the limit as n approaches infinity of 1 over radical n equals 0? Wouldn't you say, therefore converge by alternating series test? So what did I show? I showed in the blue that the series converge, and I've shown in the green that the absolute value diverge, which means this series converge but not absolutely. Conclusion out of both of those is that, therefore, conditionally convergent. That's conditionally convergent. Now I get to number 36. There's one more test I haven't used yet. You glance at that and you're thinking, okay, how does that work? If I put an absolute value, wouldn't that be the series n equal 1 to infinity? And wouldn't you say actually that this is not really equal, that's less than or equal to 1 plus n radical n and a 1 at the top? Because the biggest a sine or cosine could ever be would be the amplitude. And I'm going to take that out actually. Without the absolute value, that will be a problem. I'll show you why. Isn't that less than 1 over n radical n? We had enough practice with this. Isn't this 1 over n to the 3 halves? And isn't that a p series bigger than 1, therefore converge? What's your conclusion? Therefore, the series n equal 1 to infinity of the sine of n pi over 6 over 1 plus n radical n is what? Absolutely convergent by the comparison test. When you say absolutely convergent, you're saying you put an absolute value on it because by quoting the comparison test, the series must be positive. This series is not positive. This alternates on the coordinates. So you run from the quadrants, I meant. It goes positive, positive, negative, negative, or something like that. Pi over 6, pi over 3, pi over 2. 3 positives, 3 negative, or 6 positives, 6 negatives. Eventually, it will be negative in these quadrants. By putting an absolute value, you could quote any test that required this series to be positive, such as the integral test, the comparison test, and the limit comparison test. And there's the homework.